That's great. You guys like to learn a few things about the 60s today? Yeah. Yeah, those are good times, huh? Who remembers the 60s? Good times. Yeah? Me too. I think I was born because of the 60s. Maybe. Anyway, so first order of business today for this talk is there are two other talks going on right now in smaller rooms, in neighboring rooms. Our first order of business is to make sure that they feel sad for not coming to this talk. So what we need to do is cheer and scream and clap really loud just for a brief moment, just so they think, oh crap, I picked the wrong talk again. All right, ready? Can we do this? All right, let's do it. Go! I think that'll do it. Hopefully that does the job. Okay, so the 60s, actually, I think, was probably one of the most influential decades in shaping modern programming concepts that we use today. There were a handful of very interesting people who mostly studied mathematics and set logic and other things like that that caused us to have some of the most awesome principles we have today. There were other people that weren't so much into that, but these people in particular are the ones I'm going to talk about today. These are John McCarthy on the top left. He invented Lisp. Can I get by a show of hands anyone who's ever programmed in Lisp or one of its derivatives? Scheme, Racket, and then what's that new one that's Lispy, but not Lisp? Erlang? Was it? Erlang. Yeah, Erlang doesn't have enough parentheses, right? Close. Okay, what just happened? What's happening? Whoa. Just gonna refresh that. Hello? Oh, yeah. Okay, hold on a second. That is very strange. Okay, we're going to call back. Oh, don't tell me slides.com just pushed a change. Awesome. Thanks, guys. Okay, let's see if we can do this a different way. Yeah, we might just have to do this maybe the old-fashioned way. Yeah, looks like we will. Okay. We'll have to do this the old-fashioned way. Sorry, guys. Okay, well, anywho. John McCarthy, top left. Steve Russell. So John McCarthy invented Lisp. Steve Russell actually coded up the first two versions of Lisp. And then two other guys you might recognize. Alonzo Church in the bottom left invented lambda calculus. And Christopher Strachey, he actually was one of the first people to define the concept of a first-class function, which you rely on probably every day as a JavaScript developer. This is probably the most interesting part of this. Those four guys, actually just the first two, John McCarthy and Steve Russell, they actually implemented Lisp on that. That's an IBM 704, I think. That's what they were working with. Read eval print loop? I don't think so. Chrome debug tools? No. Right? Plugging wires in and making sure they got plugged in right? Yeah, that was the first machine that Lisp ran on. Later, they actually built a machine called a Lisp machine, which is pretty cool. It was hardware optimized to run the Lisp programming. It's very interesting. So when we talk about these concepts, you're going to think, oh yeah, that's easy. Closures, I use it all the time. These guys were doing it on that. Okay, so just nothing but respect for these people. And then just a quick shout out to this, Dijkstra, who we probably have all heard of, one of the most influential names in computer science, said that about Lisp. Thinking thoughts that were impossible to think is now possible thanks to the expressiveness of Lisp. But that's enough about the history. Let's talk about what we use today. Three concepts that I think we use every day that we owe almost 100% to those people in the 60s who invented it. The first one is garbage collection. Let's talk about that. 1959. John McCarthy's working on the first version of Lisp, and he realizes, I have this problem with memory allocation, and specifically deallocation of memory. And he says, I need the language to automatically free up my unused memory. So he says, he invented the term garbage collection for that purpose. And this is why it was a problem. So here's C, a programming language that actually didn't exist in 1959, but because they didn't learn the lessons from 1959, they had this problem with garbage collection. So here we have a function. It's just allocating 1 kilobyte of memory on the heap and then returning. If you call this function, your program now has a 1 kilobyte memory. Period, just like that. It's that easy to do. And that's what memory leaks look like. So garbage collection, it was trying to solve this problem in a way that you as a developer don't have to do anything about and automatically get your memory reclaimed. So here's JavaScript. Here we have allocated an array with 1 kilo entries in it, 1024 integers, or numbers, and return. Is there a memory leak here? No, why not? It was garbage collected, right? Now, what's interesting is garbage collection is actually a very sophisticated concept. This is not easy to do. And many programming languages punted and did an easier version of garbage collection. This JavaScript does something called tracing, where it occasionally, in the background, identifies names that used to point to data that are no longer referenceable from your program anywhere. And it automatically frees up the data referred to by those names. It's really sophisticated. Early versions of Objective-C did a much simpler version of garbage collection, which sometimes we don't even call garbage collection anymore because it's so basic, called reference counter. And the idea is that every time you pass a variable around, there's a counter hidden on it that gets incremented. And every time it gets returned, that counter gets decremented. Or you can manually increment and decrement. And if that number ever hits 0, the next tick of the garbage collector finds all of the objects that have a 0 count and frees the memory that they refer to. So that's pretty complicated too, but it's nowhere near as complicated as a tracing garbage collector, which is what we have in JavaScript today. So this makes your life a lot easier because you suddenly can allocate all kinds of data, declare all kinds of variables, build arrays, build objects, instantiate functions, and do all these things, and then just forget about it. And then the program, or the runtime, comes through afterward and finds the stuff you forgot about and frees it up. Pretty cool. 1959, John McCarthy invented that. The next concept that came out of this era is something that's called FirstClass Functions. Not every language, almost every language I'm aware of has functions. But not every language treats a function like a first-class citizen in that language. In order to be considered a first-class function, you can go to Wikipedia. In fact, as I'm going through this talk, you'll find all of the concepts on Wikipedia are very well explained, complete with history and lots of good information and examples. But a first-class function has a language that supports first-class functions has 3 properties. The first one is that you can pass the functions around as arguments to other functions. The second one is that you can return functions from functions. And then the third one is that you can assign functions to variables and in other data, in like containers or data storage, data structures. Okay, so JavaScript supports all 3 of these and more actually. So here's an example in JavaScript. I've declared here a function called counter. And the way you use it is you call it and it returns to you a function. And if you call that function, every single time you call it, it returns a new, an implemented version of a number. So you can see here, the way we do that, and we'll talk about this in a minute, is with the closure. But the counter function has a variable called n, and it's initialized to 0. That happens the first time you call the counter function. Actually, every time you call the counter function. But then we return an anonymous function that doesn't actually execute until you call it later. In this case, we just called it C. And called it, and that returns 1. Call it again, it returns 2. If I were to call counter again, I would get a new counter function that starts from 1 itself, right? So that's an example of a function that can return a function. Now, you probably use this concept every day. Maybe you don't even know it, but can you guys raise your hand if you've ever had a function in JavaScript that returns a function? Yeah, almost everybody's hand went up. This is one of the things I think is so cool about the JavaScript ecosystem, is that people in the JavaScript ecosystem, in my opinion, use principles like this. These are all actually functional principles. More so than any other ecosystem I've seen. It's pretty cool. think that's a hat tip to the language itself. Okay, here's number 2. So function as an argument to another function. So in this case, we have a jQuery call to select a button element on the screen. And then on that jQuery object, we're calling click. Click is a function, and we're passing to it as its first argument another function that we write. This one's anonymous, it doesn't have a name. Right? So we're passing it in. That makes it so that the click handler can store that and then call it if that element ever gets clicked on. Right? This is pretty basic, right? But we do this every day, and we don't think anything of it. The third property, remember, was that functions can be stored inside of other data structures. So here we are, JavaScript. An array that I call handlers that has a list of functions in it, no problem. I can even make objects whose properties point to functions, no problem. Pretty much anywhere I can store a variable in JavaScript, I can store a function instead. And then here's one that's really cool. This is actually not required, but JavaScript takes it one step further. Not only can I store functions in data structures, but I can store data structures in functions. And you do this every time you make a function constructor like this. So here I've got a function called thing, capital T for convention, and it has a this pointer, which gets set to the function itself when I invoke the thing with the new operator. So at the bottom you can see var thing equals new thing. When I call that, bottom line, this.name equals Bob, gets executed, and this.name equals that list of numbers, gets executed. And the this is the function. So not only can you return functions from functions, pass them to functions, and store them in data structures, but you can even store data on functions. Now you all knew this, but this was actually invented in the 60s. So that's pretty cool. All right, closures. Great. Can I just get by a show of hands, how many of you are familiar with the term closure and use it in my day-to-day vernacular? So awesome. So this is what's so cool. This term was invented in 1964, which, if my math is right, that actually means happy 50th birthday closures this year. 50 years of closures. Isn't that great? Congratulations. 50th birthday. Wow, that's great. I don't think JavaScript will live to 50, but closures did. So a closure is a two-part definition. It is two necessary parts. First one is that it is a reference to a function, and the second one is that it includes the enclosing environment where that function lives. Now, depending on the language, that can mean different things. But let's give some very simple examples. Here's an IFE, I-I-F-E, stands for immediately invoked function expression. Did I get that right? Expression? An IFE, I like that name. That's where we declare a function and call it immediately and then never use it again. But because we called it immediately and declared it, it has an environment. And in this case, inside of this IFE, we're declaring two things. A name variable that contains a string, and a function, or sorry, a button click handler that has a function passed into it that does something. The name is part of the closure for the function that's anonymous, that's part of the click handler. That is the closure. Now, if you think this is pretty nifty, I agree with you. Now think about this in terms of garbage collection. When can I garbage collect the name string? When can I do that? That actually makes my brain hurt. I don't know. In this case, probably never, right? Because that button could come in at any time, and the language runtime has to know that and keep track of it. So putting closures together with garbage collection, with first-class functions, leads to what I consider to be a very productive programming environment. And like I said before, the JavaScript community, and I really think this is because the language design is the way it is, has made more use of these 50-year-old language features than any other community I've seen, which I think is really cool. All right. So again, that's where this was built, this stuff. These concepts were pioneered on that kind of a machine. Oh yeah, so here's just a little nod to the 60s. Raise your hand if you get this joke. It's okay. Yes, 2 people? Yes. 3? Keep them up. 4, 5? Okay. Why aren't you just rolling in the aisles like with laughter right now? Not that funny, actually. What's that? Yeah, there you go. Okay, so see this little symbol on the top left of that machine up there? It's 2 boxes next to each other. And there's a little piece of tape covering this up a little bit. The left one has an arrow pointing down, and the right one has an arrow pointing to the right. See that? That represents a linked list, which is what list is all about. So the left-hand box is the value, and the right-hand box is the reference to the next element in the list. This machine had two registers that it used to store that data. One was called CAR, and one was called CDR. And the left-hand side is the CAR, and the right-hand side is the CDR. And anyway, people pronounce that car and cutter. So some computer science geek thought it would be hilarious to say, my other car is a cutter on the car. Awesome. Still not rolling in the aisles with laughter on that one. Maybe comedy wasn't really the 60s forte. Okay. 4 more concepts that maybe you use, maybe you don't, but you probably should be. These also came from the 60s. First one is something called referential transparency. A guy named Christopher Strachey invented the concept of referential transparency. Now, I use the term invent a little bit loosely here. These are like mathematical concepts, right? They already exist. We just discover them. So Christopher Strachey said, I want to use the term referential transparency to mean something. And the React team over at Facebook really latched onto this and considered it to be a key component of their design for the React framework. And I attribute this principle to React speed that it runs with. Anybody do React projects here? 1, 2. Man, there's like as many people with React as have written Lisp in the 60s. We should all be writing more React, in my opinion. We should really check that out. Anyway, so referential transparency. This is where it is a way to write functions such that your function, any call to your function, could just be replaced with its return value without altering the program in any way. Okay, so any function you write, if you write it in such a way that it can just be replaced with the value that gets returned from it, then you have a referentially transparent function. That's pretty abstract. Let's talk about what that means. Every single mathematical expression in math is referentially transparent. For example, I can write sine of 3 pi over 2, or I can just write -1 in any mathematical expression, and the expression will always evaluate the same result. It doesn't matter. You can interchange it, right? I could write any number of things. I squared, right, instead of -1. That sine function is totally equivalent. This is the concept that if you're going for referential transparency in your code, you want your functions to behave like too. Oh, by the way, this is really, I thought this was pretty cool. Spotlight does that. It's pretty slick. Kind of cool. All right. So here's how React uses referential transparency. So consider React like a pipeline. As input, it takes state objects. Now these states are things you define. Maybe you've got a state with like a username in it, or maybe a cookie value or something, whatever. That's a state. Probably not a cookie. Let's go with username. That is the input to, or rather React uses that as input to your render functions that you also write. And then it gets the results back, and your render functions return virtual DOM. I won't go into what virtual DOM is, but this is how React basically works. It takes state, it calls your render functions then return this thing called a virtual DOM, which is like DOM, but it's not actually in the browser, it's just plain old JavaScript object. And then React does this all the time. Anytime you tell it to render, it runs through this whole pipeline, calls all your render functions, passes in all your state, gets the results back, and it's virtual DOM. The next part isn't really related to referential transparency, but what it does with that is it compares the current virtual DOM you just returned with the previous virtual DOM, figures out what changed, and then it uses that to update the actual DOM in the browser to update what's on the screen. So consider it mathematically. F of S equals D is what they're doing here. F is your render function, S is your state from the left-hand side, and D is the output. They are totally interchangeable. Given a single state and your single render function, it will always return the same results if you're following referential transparency. It will always return the same results. So you can just have the results, or you can call the function again and get new results. But if you already have the results from the previous day, you don't have to call the function, you already have it. Right? So that is what referential transparency is all about. Now I'll talk about some of the benefits of this a little bit later, but the benefits of referential transparency include many of the same benefits that functional programming gives at large. Okay, next topic. This is by far one of my favorite topics that came out of the 60s, and I can't for the life of me figure out who invented this thing. And I think that's because the concept actually goes way back to the late 1800s, maybe the early 1900s, when people were just barely defining what the word function even means. Now this is way before they had computers to execute functions. This is actually way before anyone even thought, oh, we have computers and we have this mathematical concept of a function, maybe computers should run functions, because the first ones didn't. So function composition, it probably was popularized by a guy named Haskell Curry. Raise your hand if either of those two words is familiar to you, Haskell or Curry. Raise your hand if only one of those is familiar to you. I'm curious. Yeah, cool. Is it Curry or Haskell? Haskell? Okay. This guy was so influential that he has had, I think, 4 programming languages named after him. I don't know how you get 4 different languages out of that name, but they did. The most popular one is Haskell, and it's not very popular. And currying is another concept that we're not going to talk about today, also named after him. Really cool. So, I think he probably popularized the notion of function composition. Here's how it works. First, let's get a little bit mathy, and this will be the last mathiness we do today. Function composition is the ability to nest your function calls so that the return value of one gets passed as the input to the next, and so on and so on. You can do this ad nauseam. Here we have 2 functions, f and g. We're passing a parameter to g called x, and whatever g returns when you pass it in x gets passed as the input to f, and then f returns some value too. Okay, does that make sense? So sometimes you say this as f of g of x. Everyone's like back in junior high now going, oh, we did that. So let's talk about how we do that in JavaScript. First of all, how you don't do function composition is like this. Let's say someone comes to you and says, I need a function that capitalizes all of the words in an array. You're like, great, I know exactly how to write that. I'll call it capitalize, it'll take a single argument, that's the array, it'll write a for loop that goes through each array element, and capitalize it. Done. Right? This is what I would have written if someone said, write a function that capitalizes an array. But this is a single-purpose, non-reusable function that really can't be used for anything else, right? And if someone says to you, oh, now I need a function that does something else to an array, you're going to rewrite that for loop, right? You're going to write a new function, a new for loop, and the only thing that's going to be different is that one line in the middle that assigns each element, right? But the key here is not composable because it doesn't return anything, and it mutates its input. It's actually modifying the contents of the array. This is not a composable function. The difference is subtle, but I think really, really important. Here's a composable version. So I factor it out into 2 functions. First of all, I write a function called upper that just takes a single string and returns a new string that's capitalized. Okay, that's that first function. By the way, that is returning a new string. That is not uppercasing the string in place. That is returning a new one. We'll talk about that in a minute. Then my capitalized function is really cool. I take a listen, and what do? I return a new list, a new array, that just maps that upper function to all the elements of the input array and just returns a new one. Okay, why is this better? First of all, no for loop. That's cool. For loops introduce state into your function, state that you have to keep track of. It's got an iteration counter, right? Secondly, it returns a list, a new one. It doesn't mutate the original. As a result, I can chain these things up. So if you wanted me to capitalize all the elements in an array, and then title case all the elements in the same array, and then remove elements that don't match a certain pattern, and yada, 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 I can just chain those all up. Just f of g of x, right? Capitalize, pass in, remove elements, pass in, title case, pass in the list. Just like that. Each one of them can be independently unit testable. And if you write a unit test like this, you don't have to worry about maintaining the state of the array because the original array is never modified. So you have one array, you can call these functions on it and verify that they return a new one. Very nice, very black box. That's function composition. Here's some great reading down here, by the way, on function composition in JavaScript. So when you're making these little day-to-day decisions, how do I write this function? Consider it in this game. Consider composition always. If you don't want to do composition, that's fine. But think about what the side effects are going to be. Okay. Oh, performance. So what do you think is faster? To do this or that? What do you think? This one is probably faster? The first one? The composition is probably faster? Yeah, it's really hard to say. I actually haven't measured this. But it depends. It's going to depend a lot on your JavaScript runtime on how good it is at allocating new objects. Because this one is going to allocate n new strings, where n is the number of elements in your input list. This one is just, well, actually it's going to make n new strings also, but it's not going to have to allocate a new array. So it really depends. The fact of the matter is that most runtimes these days are optimizing for this, which is great. They're optimizing for lots and lots of allocation and t-allocation. They're optimizing for functional style programming, just like this, because functional programming does this kind of stuff. They allocate objects out the yin and throw them away and never ever write them again. Okay, here's something that's really cool. Who here has used promises in JavaScript? Okay, yes, that is so good. I'll bet if I had taken that same poll 3 years ago, people would have been like, what's a promise, right? Who's been using promises for more than 3 years? Probably nobody, no, one person, good, early adopter, yeah. Were you born in the 60s?
I was.
Promises use function composition. It's actually promise composition. It's not really functions. There are functions involved, but what you're supposing is promises. Here's an example from jQuery. So jQuery has the get function, right? I can get a URL, and then what that returns is a promise. A promise has a then method on it, right? And when I call then, I can pass in a new function, and then returns a new promise. And then I can call then on that promise, and that returns a new promise. And you can chain them up. That's why you can chain these up. And at this point, the original promise, you don't have it anymore, it's gone. But what you do have is a new promise that works just as well. It comes out of the back of the then. This is immensely powerful. It's very, very subtle, the difference between this and just passing a callback function in as the second argument to your get call. Very, very subtle, but this is vastly superior. And this article down here, I recommend when you get a minute, I'll send out links to the slides. Take a minute and read that article. This is someone criticizing the Node community for choosing to do continuation passing style instead of promises for all their callbacks. He makes some really good points, but what it basically comes down to is passing in a callback function is imperative. Passing or returning a promise is declarative and composable and functional. It makes a big difference. It's really cool. Definitely recommend it. All right, lazy evaluation. Has anyone heard this term before? Lazy evaluation? Good? Yes? Great. Lazy evaluation is pretty powerful. The earliest reference I could find for this term was 1976, so we kind of left the 60s a little bit. The idea behind lazy evaluation is that I can have an expression, and maybe it's a computationally expensive expression to evaluate, but I don't need to evaluate it immediately when I declare it. I don't need to evaluate it necessarily when I pass it off to other functions. I only need to evaluate it at the very final moment when someone needs to get the value of that function. Okay? There are two reasons for this. You can get improved performance by only evaluating the subset of expressions in your program that need to be evaluated. Or the other advantage is you can actually, with lazy evaluation, construct infinite data sets. Let's say you want an array that contains all prime numbers. Right? That's an unbounded infinite data set. But you can write a lazy function that returns the next prime, and it can act like a data set. It can behave kind of like an array. And it just won't actually compute the next prime until you ask for it. Okay? So here's an example. Oh, here we go. Finding primes. Everyone loves to find primes in their programs. Everyone ships prime finding to production, right? That's like pretty common. It's like the first function you write in your code usually. So the eager evaluation, the opposite of lazy is eager. The eager evaluation version of finding an next prime is simple. You pass in a previous prime and it does lots of work and it returns the next prime. That's eager. That just evaluates it right away. The lazy version, in JavaScript at least, would probably look something like this. You pass in the previous prime, and what you get back is not the next prime, but rather a function that you can call whenever you want, if you ever want, the next prime. So if you have an expensive operation, and maybe you have a data set that's enormous and you're only ever going to look at a subset of it, you can pass around functions instead of values. And if the functions are referentially transparent, you can substitute the values and the functions interchangeably, and boom, you can just do it just like that. In some cases, the caller may never actually need the result, but they needed to get the ability to call the result if the user decides they want to make it. So it turns out JavaScript is actually not that great for lazy evaluation. I found a couple of projects. I think there's one called lazy.js, where people are trying to introduce lazy evaluation patterns, but it's really not well supported at the language level. And the reason it's not well supported is because JavaScript doesn't really have operator overloading and classes and things where you can treat variables like you can, for example, in Python. In Python, this is an example from the Django project. In Python, I can say, hey, Django, I want you to translate the string hello world. What that does is, under the hood, translating a string is a matter of looking up in a file that has a lookup table, all the English strings, locating the one you want, and returning the language translated version of that string into whatever language you want. It's not super cheap to do that, because you have to go look this stuff up. Even if you have it in memory, you still have to go do the lookup. It's not as simple as just assigning a string. You have to go look it up. So the Django project opted to create a lazy version of this string, or of this function, rather, that instead of returning the translated string, it returns what they call a lazy string. And a lazy string is one that just contains a closure that gets evaluated when you actually try to read the string. So in the case of Django, when I call this function, this translated string object that I have, until I actually try to display that string or read its contents, it will not go look at that lookup table. And this is great because you could have thousands and thousands of strings in your project, and Django won't go translate all of them up front when the project loads. Instead, it will translate them as the user reads them, which is pretty cool.
So if you were to call type on translated string, what
Yeah.
would it be?
Lazy string. Yeah. Django has a module called django.utils.functional, and in their functional, there's that word again, they have this thing called a lazy string. They can actually lazify any type. It's pretty cool. Yeah, and that's it. So I thought that was pretty cool. I am unaware of any JavaScript language construct that will allow you to do something like this, which is kind of sad. Yeah.
Object getter and setter.
So, yeah, okay. But how do you make it so that when I read a string that happens? I guess you'd have to make your own string class or something.
It'd have to be a property. I don't think it could be
The
a
value
freestanding. It couldn't be a freestanding variable. It'd have to be an object, and then you call it.
So you have to, if you're doing it with strings, you have to replace all your strings with these objects that have like a dot value or something. And then they don't actually evaluate the value until you call the dot value. But yeah. So, and that's effectively what Python did with theirs, except they have a little bit more power because they let you do, you can overload just call. So anytime you see this call. And in the case of strings, they have this repr function, REPR, and anytime you try to read it, it gets called, and so it's returned. So anyway, there you go. Lazy evaluation. I actually, since we have, how much time do we have? 15. Okay, I want to tell a brief story about Haskell. Haskell built lazy evaluation into the language. Now I'm no Haskell expert, but they have some really cool stuff. I can write a function in Haskell that returns an infinite data set, and by default, it will only evaluate the pieces of that data set that you actually try to read. This is pretty cool. So a friend of mine was taking a programming languages course at the U, and they were tasked with creating some kind of game. I don't think it was chess, but it was some kind of board game like chess. And one of the students chose to use Haskell to build this game. And the game was supposed to look ahead and do kind of an AI thing, like a weak AI, to try to look ahead and choose moves depending on what would be the best approach. Well, in the game of chess, and in this board game too, there are 2 to the 64th possible ways to lay out the board, and every time you lay out the board, you have an enormous number of options for which pieces to move and what those ripple effects will be, right? So it would actually be impossible in today's computers to store all of the possible moves and permutations, moves and counter moves, and then evaluate all the best ones and try to figure out what the best course of action would be, right? But in Haskell, you can do exactly that. You write a function that defines what all the moves can be. Haskell doesn't actually evaluate all of them, but as you go around the board, your program just automatically lazily evaluates the next steps here and there. And his program ended up being enormously faster than the other students' programs, which I thought was pretty cool. Yeah, it was pretty slick. All right, immutability. This is another one that I can't tell when this concept was introduced into the world. If anyone knows, that would be great information, but I really don't know. But this is right at the heart of functional programming, and it probably came from Lisp, and Lisp came from the 60s, because pretty much everything that you do is Lisp at the end of the day. It's all inspired by Lisp. Much of what we do anyway. Here's a definition of immutability. Objects can be created, but you can never change them once they've been created. Okay? This applies to variables, objects, arrays, anything. If you change the value of what a variable points to, you have mutated. That is not allowed if you are going to be writing an immutable program. So an example of this, I've got an X object here that just has a single property called name, and I try to change it. Not allowed. Now JavaScript does allow this, right? I mean, big deal, we do this all the time, right? But that is a mutation. So if you write your code in such a way that you never mutate it, you get lots of benefits. It is much, much easier to unit test code that doesn't mutate its state. Much, much easier. Concurrency is way easier, right? If you don't have to worry about two threads or two processes modifying the same data at the same time, you don't have to do all kinds of thread synchronization and locking, right? Also, you can get higher performance because there doesn't need to be any cross-thread communication synchronized between each other. There are no side effects. When I call a function and say that function alters the state of a global variable, as a caller, I can't really tell that that happened, but it happens, right? We've all had that happen. Suddenly, I call a function, all I wanted to do was get the name of some user, but what I ended up with is I edited some global state somewhere, and now my next function call assume that state wasn't changing, and boom, everything blows up, and I got to trace and figure out what happened. And lastly, you can do the flyweight pattern. Has anyone here heard of flyweights? It's we all use it every day, but I haven't really heard it used by name. The idea behind flyweights is that if I have two variables who point to data that is the same, the runtime can just store that data once in memory instead of storing it in two different places. And if I have 3 and 4 and 5 variables, they all just point to the same piece of memory. That's called flyweights. Here's an example of flyweights in action. I've got X variable that I assigned to Fred. I have a Y variable that I assigned to Fred, and I ask them if they're equal with a double equals operator, and of course they are because they have the same characters. But then I ask JavaScript if they are triple equals, which means they are the same object, and that is also true. They're the actual exact same object. Under the hood, JavaScript detected, oh, you already used the name or the string Fred. I'll just point your Y variable to the same place. Okay, so JavaScript strings already are immutable. You cannot edit a string in JavaScript. Can't be done. Does anyone disagree? I'd love to hear it. You can't do it. Has anyone tried to change a character in a string? Like just replace it with a new character? How did you pull that off? Anyone? No, seriously, like, how do you do it?
Index in. You try to index in with the, brackets and
Yeah.
5.
And what happens?
I don't remember. I haven't done it in years.
It just silently ignores it. It's like, it's like if you do like string, bracket, 5, bracket, equals, some new character, it's just like, whatever. Silently ignores. Kind of sucks. So the way you actually do that, let me give you, I'll tell you that in a second, but a couple of examples. First of all, I've made a string called str and assigned it to Bob likes apples. I then tell the string to replace the word apples with the word oranges. And what does that do? I would actually expect it to go into the string, take the word apples out, and put the word oranges in, but it doesn't. Instead, it returns a whole new string. Except this string has the characters replaced that you asked for. Okay? And if I look at the original string, it still says Bob likes apples. So there you go. Same thing is true of the slice function. If I have a string called joke is funny, and I try to slice out the characters 4 through 12, that returns those characters is funny, but the original string, not modified, because the language says you can't. So JavaScript made that decision for you, but not all JavaScript types are like that. For example, arrays, totally mutable, right? Objects, totally mutable, no problem. Functions, totally mutable. So JavaScript just can't do it on objects in general, right? Right? Or can it? Oh, who just said it? Yeah, object.freeze. Had no idea this existed. So talk about a bolted-on feature, right? So if I have a variable x and I assign it to an object with a name property, and then I tell JavaScript to freeze it, and then I replace the name property with a new string, what does JavaScript do? Silently fails. If I read x.name, it's still there. It's still there. Isn't that great?
Why doesn't it grow?
So if you want to play a trick on your coworkers, just slip some of those into their code and blow their minds. Anyway, that's a good one. Has anyone used this in production? No. Yes? Can you tell us use case?
Yeah, I used it as a way to maintain some constant variables that I didn't want to change.
Oh, nice. Good idea. I'm going to do that. I've got some constants right now in my project at work. And the cool thing is object.freeze actually returns the object. So all you got to do is just put object.freeze as a wrapper call around your object, and poof, it's now a constant. Yes.
It's
Nice.
shallow.
What's that?
Shallow.
No, of course it's shallow. So if I said like x.name dot something else, not frozen, curse you, it was almost an awesome feature.
There's a few browser compatibility issues.
Yeah, I'm not surprised. Given that only 2 people in this room even knew it existed, I'm not surprised that browsers implemented it differently. So, anyway, not making a suggestion on that anyway, but immutability is largely considered to be a desirable property of programming in general. The less mutation of anything you have in your program, the easier it will be to reason about, possibly higher performance, and definitely more testable. There you go. There are 3 other concepts that I don't really have time to go into, but I wanted to talk about just briefly. These all came from the days of yesteryear, in the 60s as well. You probably don't use any of these. The first one for sure, because JavaScript simply doesn't support it. But has anyone here heard of tail recursion before? Great. So the way that the JavaScript runtime works, every time you call a function, the runtime has a stack that it keeps in memory. That stack, the elements on that stack represent every function that is called and the depth. I'm kind of saying that badly. It's not a journal of all functions that were ever called. It's in the current context, which function called me, and which function called that, and which function called that, all the way back to the main function, which is like your root, the page's script, in the browser anyway. And that's a stack, right? So when one function returns, it pops an element off the stack, and so on. Now this concept of a stack goes back to antiquity. The very first time I think functions were implemented, well, maybe it didn't, I don't know. There were call stacks. I think in the early days of subroutines, there were not call stacks. In fact, Fortran doesn't have the notion of recursion at all because they never thought you need to call yourself. You call your own self back. And as a result, I'm not sure how its stack works. It probably doesn't work like a modern call stack. But anyway, that was a little bit of an aside. With tail recursion, the idea is if I have a function foo, and inside the body of foo, I call foo again, that's going to push an element on the call stack, right? And every time I call foo, within that foo, I'll get another call stack element. Boom, 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 and up it goes. Well, there's a certain class of functions where that's actually not required. Like, let's say I'm writing a function that's just traversing a tree, but I'm never backtracking. I don't need a call stack. And some languages will actually figure that out by looking at your code and saying, oh, you don't need to keep track of the call stack. And so it just won't push new frames on the call stack every time you call. And that's called tail recursion. And the benefit is you can do infinite recursion on data structures without ever blowing your stack. Anyone had a Stack Overflow error because they wrote infinite recursion? Yeah. With tail recursion, there's no such thing as a Stack Overflow if you write a function. Now, if your function actually, each function returns a value, then you can't have tail recursion. So anyway, it's a static analysis step that the language will do to figure out if you can have tail recursion. The other thing we didn't talk about today is side effects. Side effects are when you write a function and the function does something, mutates state of variables outside the scope of that function. That's called a side effect. And it is generally considered less desirable, especially in the functional world. totally undesirable in functional mode. But that's a side effect. That notion came out of this era too. And the last one is pure functions. A pure function is actually one that is a lot like a referentially transparent function. It's one that only operates on its inputs, returns a value. The value it returns always, for any given input, it always returns the same output. And that is a pure function. So also that came out of this era. All right. So basically, functional programming was born during this era, over 50 years ago. And only really now is it coming back into popularity. People are starting to say, yeah, let's do this. Languages like Scala and so on are coming back. There are two talks that I think, if you're interested in this subject, you should definitely watch. They will change the way you program in subtle, small ways, but will have big consequences for your program. The first one is a talk by Gary Bernhardt, who is known for his talk WAT. You guys seen the WAT talk? Yeah, that's Gary Bernhardt. He wrote a talk called Boundaries. Fantastic talk. He talks about a proposed way to structure your program such that you can use functional principles, but where they don't work around the perimeter of your program, you can use imperative principles there. And then this other really cool article, actually from IBM, about why functional programming is coming. Also, here we can see the influence of the 60s on 4 modern languages, the most modern of which is Swift. Has anyone looked into Swift much here from Apple just last week? Or this week? It was Monday, right? They announced it. Was it? It was Monday, wasn't it? Yeah, last week. Okay. My mind's been in the 60s. I haven't really been paying attention to anything. So Swift has some really cool functional features built right into the language. Clojure, which is a Java-based language, Scala also Java-based, and Microsoft has theirs called Visual F#. Anyway, the 60s were, in my opinion, awesome. And many of us, I think, take for granted that we have these concepts that we use every day to make us super productive, make us able to produce applications at a speed we've never been able to anticipate in the past, thanks to the pioneering work of people not like that in the 60s who worked in very small rooms filled with buzzing loud computers and plugged wires into each other and studied math intensely. That is why I think the 60s are awesome. Thanks, everyone.